Welcome to an exploration of quantum tunneling devices that operate in a seemingly faster-than-light regime at the nanoscale. At the nanoscale, electrons can tunnel through energy barriers in devices called tunnel junctions, exhibiting the mysterious Hartmann effect, where transit time barely increases with barrier thickness. Let us first understand why quantum tunneling defies classical physics intuition. In classical mechanics, a particle with insufficient kinetic energy cannot overcome a potential barrier taller than its total energy. It would simply bounce back. Here we see a classical particle approaching a potential barrier. The particle's energy E is less than the barrier height V, so classically it must be reflected. The barrier region is absolutely forbidden. When the particle energy E is less than the barrier potential V0, classical physics predicts complete reflection with zero transmission probability. However, quantum mechanics reveals a startling truth. Particles have a non-zero probability of appearing on the other side of the barrier through a process called quantum tunneling. To understand tunneling, we must describe particles as quantum wave functions. A free quantum particle is described by a wave function psi of x and t, which oscillates with wave vector k and angular frequency omega. The energy E equals h bar omega, and momentum p equals h bar k, connecting wave and particle descriptions through Planck's constant. The quantum wave function spreads out in space, representing the probability amplitude for finding the particle at different locations. The wave oscillates and has extent in space. When a quantum particle encounters a barrier where its energy is less than the potential, the wave function doesn't abruptly stop. Instead, it penetrates the barrier with exponentially decreasing amplitude. Inside the barrier, the wave function amplitude decreases as e to the minus kappa x, where kappa is the decay constant proportional to the square root of the energy deficit V0 minus e. This graph shows the wave function amplitude inside the barrier region. It decays exponentially from left to right. If the barrier is thin enough, some amplitude survives to emerge on the other side. The probability of tunneling depends critically on the barrier width and height. The transmission probability T approximately equals e to the minus 2 kappa d, where d is the barrier thickness. This shows exponential suppression with barrier width. Let us calculate a concrete example. Consider an electron facing a 1 nanometer barrier where the energy deficit is 1 electron volt. Using the electron mass and Planck's constant, we calculate kappa to be approximately 5.1 times 10 to the 9th per meter, or about 5 per nanometer. For our 1 nanometer barrier, the transmission probability is roughly e to the minus 10, or about 0.004%. Small, but definitely non-zero. This plot shows transmission probability versus barrier thickness. Notice the dramatic exponential drop-off. Adding just a few nanometers can reduce transmission by orders of magnitude. Now we encounter the puzzling Hartmann effect, where tunneling time seems independent of barrier thickness. A natural question arises: how much time does it take for a particle to tunnel through the barrier? This seemingly simple question leads to profound mysteries. Physicists define tunneling time using the phase shift method or group delay, measuring how long a wave packet takes to traverse the barrier. The tunneling time tau is defined as the derivative of phase shift phi with respect to frequency omega, representing the group delay of a wave packet. Thomas Hartmann discovered in 1962 that as barriers become thicker, the tunneling time does not increase proportionally. Instead, it reaches a constant saturation value. For thick barriers, the tunneling time approaches a saturation value tau sat, approximately 1 over kappa c, regardless of how much thicker we make the barrier. This remarkable graph shows tunneling time versus barrier width. The time increases initially, but then saturates at a constant value, seemingly independent of how thick we make the barrier. The Hartmann effect raises an urgent question. Does this violate Einstein's speed limit, the speed of light? If the tunneling time saturates while the barrier gets thicker, doesn't that mean the effective speed increases without bound? Could we send signals faster than light? The answer is definitively no. While the tunneling time saturates, remember that transmission probability drops exponentially with barrier thickness. The effective velocity d over tau may approach infinity, but the transmission probability t simultaneously approaches zero exponentially fast. To detect a signal, you need measurable transmission. For thick barriers, so few particles tunnel through that no practical signal emerges before noise overwhelms it. The signal-to-noise ratio is proportional to transmission probability, which vanishes for thick barriers. Thus, no information actually propagates faster than light. The peak of a tunneling wave packet may appear to move quickly, but causality is preserved. The leading edge of the wave packet, which carries information, never exceeds the speed of light. Let us calculate actual tunneling times for realistic nanoscale tunnel junctions. Silicon dioxide is commonly used in electronic devices. Consider a 3 nanometer thick silicon oxide barrier with a barrier height of 3.1 electron volts. An electron with 1 electron volt of kinetic energy approaches this barrier. The energy deficit is 2.1 electron volts. The decay constant kappa equals approximately 7.4 times 10 to the 9th per meter for this energy deficit. The saturation tunneling time is approximately 0.45 attoseconds, an incredibly short timescale where the Hartmann effect becomes significant. If the electron could classically traverse 3 nanometers at typical velocities, it would take about 10 attoseconds. The tunneling time is even shorter. The effective speed becomes approximately 6.7 million meters per second, which is about 22 times the speed of light. But remember, this is not a usable signal speed. Resonant tunneling diodes exploit quantum effects to create ultra-fast electronic switches. A resonant tunneling diode consists of 2 thin barriers separated by a quantum well region where electrons can have discrete energy levels. The double barrier structure creates a quantum well between the barriers. When electron energy aligns with a resonant level in the well, transmission dramatically increases. At resonance, when the incoming electron energy exactly matches a discrete energy level in the quantum well, the transmission probability can approach 100%. The transmission has a Lorentzian resonance profile with width gamma and peak at the resonant frequency omega 0. This is the resonance transmission curve. Notice the sharp peak when electron energy matches the resonant level. This enables voltage-controlled switching. Resonant tunneling diodes can switch on and off in less than 1 picosecond, making them among the fastest electronic devices ever created. Modern electronics push tunnel barriers to atomic scale thicknesses where quantum effects dominate. Flash memory devices use tunnel oxide layers just 1 to 2 nanometers thick, only a few atomic layers, to control charge storage. The tunneling current density J decreases exponentially with barrier thickness D. Even a single atomic layer difference dramatically changes current. At high electric fields across these ultra-thin barriers, Fowler-Nordheim tunneling becomes the dominant transport mechanism. The Fowler-Nordheim current density depends on electric field E and barrier height V0 through this exponential relationship. Why do thinner tunnel oxides enable faster device operation? This connects directly to the Hartmann effect. Thinner barriers provide exponentially higher tunneling current and shorter transit times. Both effects combine to enable faster charge transport and faster device switching. For thin barriers, tunneling time increases with thickness, but as barriers get thick, time saturates. Engineers want to stay in the thin regime for speed. One of the most remarkable applications of quantum tunneling is the scanning tunneling microscope. The STM operates by positioning an atomically sharp metal tip within about 1 nanometer of a conducting surface, allowing electrons to tunnel across the gap. A sharp metallic tip hovers above a surface with a gap of roughly 1 nanometer. Electrons tunnel across this vacuum gap, creating a measurable current that depends exponentially on gap width. The tunneling current varies exponentially with tip surface separation S. A tiny change in distance, even 1/10 of an angstrom, produces a measurable current change. This exponential sensitivity means the tunneling current changes by roughly a factor of 10 for every angstrom change in height. This allows atomic resolution imaging. By scanning the tip across the surface while monitoring tunneling current, the STM creates maps showing individual atoms, revolutionizing surface science and nanotechnology. The meaning of tunneling time remains one of quantum mechanics' most debated conceptual puzzles. A deep question. When a particle tunnels, is it actually present inside the classically forbidden barrier region? What does that even mean? Physicists have proposed many definitions of tunneling time: phase time, dwell time, Larmor time, Bodecker-Landauer time. Each gives different results. Phase time measures phase accumulation. Dwell time measures how long the wave function resides in the barrier. Larmor time uses spin precession. All differ. The fundamental issue is that time in quantum mechanics is not an observable operator like position or momentum. There is no unique quantum mechanical time operator. Recent weak measurement experiments suggest particles may take complex paths through barriers, sometimes appearing to traverse them instantaneously, sometimes taking extended times. The physics community agrees that no information travels faster than light, and causality is preserved. But the precise meaning of tunneling time remains philosophically subtle. Despite theoretical puzzles, engineers successfully exploit tunneling in practical devices. Tunnel FETs use band-to-band tunneling to achieve lower switching voltages than conventional transistors, potentially enabling ultra-low power computing. In a tunnel FET, electrons tunnel through a potential barrier between source and drain. The steep band-to-band tunneling enables sharper switching than thermal emission. Superconducting Josephson junctions rely on Cooper pair tunneling through thin insulating barriers, forming the basis of superconducting quantum bits for quantum computers. The supercurrent through a Josephson junction depends on the phase difference delta between superconductors. These AC-Josephson relations govern quantum circuit behavior. Quantum cascade lasers use electrons tunneling between quantum well subbands to emit terahertz and infrared radiation, with applications in spectroscopy and imaging. Single electron transistors control current flow one electron at a time using Coulomb blockade and tunneling through nanoscale islands, approaching fundamental quantum limits. Understanding the forbidden speed regime allows engineers to design devices operating at fundamental quantum limits. With carefully engineered ultra-thin barriers, electron tunneling can occur on timescales below 100 attoseconds, approaching the fundamental speed limits of electronic response. Maximum operating frequencies approach 1 to 10 terahertz when tunneling times reach the attosecond regime. This represents the frontier of electronic speed. This plot shows maximum frequency versus barrier thickness. The green region represents the practical design window, where tunneling is fast enough for terahertz operation, but current is still measurable. Engineers face a fundamental trade-off. Thinner barriers give faster response but lower current. Thicker barriers give more current but slower response and saturation. For most practical applications, optimal barrier thickness falls between 0.5 and 2 nanometers, balancing adequate current with attosecond scale switching speeds. Real tunneling devices operate in environments that cause quantum decoherence, affecting the forbidden speed regime. In real materials, electrons interact with lattice vibrations called phonons, crystal defects, and thermal fluctuations. These interactions destroy quantum coherence. The quantum coherence time is approximately h-bar over kBt, where T is temperature. At room temperature, this is only about 25 femtoseconds. To observe purely quantum tunneling behavior, the tunneling time must be shorter than the decoherence time. Otherwise, classical-like incoherent hopping dominates. For tunneling times of 0.1 femtoseconds, coherent tunneling persists up to about 400 Kelvin. Faster tunneling allows room temperature quantum coherence. This diagram shows a tunneling electron losing coherence as it propagates. Interactions with the environment gradually destroy the quantum phase information. Many advanced quantum devices operate at cryogenic temperatures below 4 Kelvin to preserve quantum coherence over longer timescales, enabling more complex quantum operations. How do scientists experimentally verify these ultra-fast tunneling times? Attosecond laser pulses, the shortest controllable light pulses ever created, allow direct time-resolved measurements of tunneling processes. Scientists use pump probe spectroscopy, where one attosecond pulse initiates tunneling, and a second pulse probes the electron's position at different time delays. The time resolution equals wavelength over the speed of light. For extreme ultraviolet pulses of 30 nanometer wavelength, this gives roughly 100 attosecond resolution. A sharp metallic tip hovers above a surface with a gap of roughly 1 nanometer. Electrons tunnel across this vacuum gap, creating a measurable current that depends exponentially on gap width. In conclusion, quantum tunneling devices operate in a forbidden speed regime, enabling ultra-fast electronic switches and opening doors to new technologies.